Hello juniors, today we're going to continue with electronic assignment 17, which is about trigonometric functions. Today we're going to see the second part of all of this. If you remember from last class, we have seen the two of the most important trigonometric functions, which are the sine and the cosine function, which graphically look like this. We have seen some characteristics of both functions. Remember, three basic things you need to remember about these functions are where each of these functions begin. Remember, a cosine begins at its maximum point, while sine begins at 0, 0. This is whenever we're talking about a parent function without any type of transformation. Then we have seen the period. We've seen that both functions have a period of 2 pi when they have no transformation. And finally, the amplitude, which is the distance from the axis of the function to one of its maximum or minimum points. Whenever the trigonometric functions have no other transformation, the amplitude for both sine and cosine functions is equal to 1. Okay, we have performed some investigations about this. We've seen some examples about this, and now we're going to do a second investigation, and then we're going to generalize all of the transformations for sine and cosine. So it says, use technology to help you sketch the graphs of the following functions. And we're going to graph all of this 4 over here. Sine of x, then sine of x plus 2, then sine of x minus 2, and sine of x minus 1. What do you think should happen in each of these cases described here? If you remember from transformations, the content we've seen at the beginning of the year, you will remember that whenever we add or subtract a value inside the parentheses where the x is, we're having a horizontal translation, right? So let's graph these functions. I'm going to use Desmos. The first is sine of x. Then we had sine of x minus 2. Sine of x minus 2. You see here a difference, right? Let me erase this for a second. This is the original sine function. And if I draw the other one, you'd see that it is displaced 2 units to the right. Okay? Instead of starting here, it now starts here, right? 2 units to the right. Then the maximum, for example, we have a maximum right here, and the new maximum is now here, 2 units to the right again. So all of the function is displaced 2 units to the right. Then if we do the opposite, sine of x plus 2, you would see that we have the same situation, but now the purple function moved 2 units to the left, right? And finally, the other example, I think it was sine of x minus 1, but it's the same thing, right? Sine of x minus 1, and you would see that all the function is displaced 1 unit to the right in this case. Okay, so that's the new thing about this. Let's go back. It says, how does the value of c in y equals sine of x minus c transform in the graph of sine of x? So we know, right? The value of c produces a horizontal translation. Horizontal translation. Okay, and then for the second part, we're going to see this case. It says, sketch the graphs of the following functions, sine of x, then 2 plus sine of x, 3 plus sine of x, and negative 1 plus sine of x. If you remember from transformations, you would remember that whenever we have a number added outside of the function, we're producing a vertical translation, right? This is the same as saying sine of x plus 2. We can invert the order of this, for example, and the function would be the same, right? So let's see how they look when we graph these functions. We're going to leave sine of x. Then we have, for example, 1 plus sine of x. You would see that the function, the red one, now moved 1 unit up, right? Instead of being in its original position, all of the points have moved 1 unit up. But it's only a vertical translation, not a horizontal translation. Then if I do, for example, negative 3 plus sine of x, you should see that the function should move 3 units down, right? You see that? And if we do what was another case? Let's see, 2 plus sine of x. It'll be the same thing, right? 2 plus sine of x. And you would see that the function now is displaced 2 units up with respect to the original function, right? If I erase this, you would see this clearly. So for example, the origin in the original function is 0, 0, but in the transformed function it would be 0, 0, 2, right? The y coordinate moves 2 units up. The maximum, the original was 1 for the y value, and now it is 3 for the changed function. Okay, so to generalize this situation, it says y equals sine of x minus c or y equals cosine of x minus c translates the function c units horizontally, right? If the value of c is positive, it would move to the right, and if the value of c is negative, it would move to the left. Then it says y equals sine of x plus d or y equals cosine of x plus d translates the function d units vertically, which is the second example we've seen here. Okay, so now the important part of this class, the general sine or cosine function. This is how we can generalize any trigonometric function by applying all of the different transformations we have seen in the previous investigations. Y equals a times sine of bx minus c plus d, where the absolute value of a, this number over here, is the amplitude. Remember that the amplitude can also be found by doing maximum value minus minimum value divided by 2. Then we have the period of the trigonometric function, which is found by doing 2 pi divided by b. Then we have c, which represents a horizontal shift, and finally d, which represents a vertical shift. The vertical shift can also be found using this formula, right? Maximum value plus minimum value divided by 2, which represents the average value between the maximum and the minimum. So this is how we present both general functions. Basically, it's the same we have here. And here we have a summary of what each letter represents. A represents a vertical stretch. The amplitude of the sine or cosine function will be equal to the absolute value of A. Remember that the amplitude should always be a positive number. That's why we have an absolute value here. Then, B represents a horizontal stretch, which affects the period of the function. The period of the sine or cosine function will be equal to 2 pi over the absolute value of B. The period should also be a positive number always. Then C represents a horizontal translation or shift. Then the function will shift to the right if C is positive and to the left if C is negative. And finally, D represents a vertical translation or shift. The function shifts up if D is positive or down if D is negative. So here you have a visual representation of all of what each of these letters causes to the function. Okay, so the following part is a step-by-step process to sketch any type of circular function. This is very important for you to know in case of paper 1, where you're not allowed to use your calculators. So these are some steps to follow. Number 1, it says, identify the amplitude and the vertical translation to determine the axis of the function, the maximum and minimum values. Number 2, identify if the function is sine or cosine, and the horizontal translation to determine the position of the origin point. Number 3, calculate the period to plot the remaining points. Midway between two maximum values, there's a minimum value. Midway between a maximum and a minimum value, there's a point on the axis of the function. And finally, number 4, connect the points by hand. We would never use a ruler here because remember that trigonometric functions are waves, right? They are not straight lines. Okay, so let's see this example. It says, sketch the graph of the function y equals 5 cosine of 2/3 times x plus pi minus 2. So we're going to follow these steps. The first step, number 1, as you can see, it's identify the amplitude and vertical translation. So if we take a look at this function, you should already identify that the amplitude, let me do this with black, the value of A is the amplitude, and this is equal to 5, okay? So this is amplitude. Then we need to determine the vertical translation. From this function, we see that the value of D represents the vertical translation, and that value is equal to -2 in this case. So we know that this function has a vertical vertical shift 2 units down. 2 units down. Okay, so with these two pieces of information, we can start plotting our graph. I'm gonna make this, if the value of a is 5, the amplitude is 5, and the axis of my function is -2, then my maximum value would be +3, while my lowest value would be -7, right? Because from -2 we go 5 units up and we end up in 3, and from -2 we go 3 units down and we end up in sorry, not 3 units. We go 5 units down and we end up in -7. Okay, so that's how we can determine our maximum and minimum values of y. Okay, so I'm gonna make my coordinate plane here, and we're going from, let's see, our maximum value, we said it's 3, so 3, 2, 1, then we have 0 right here, then -1, -2, -3, -4, -5, -6, and -7. Okay, that's fine. Let me erase this small part here. There. So this is y, and for x, I'm gonna go pi by pi. Okay, so this would be pi, then this would be 2 pi, 3 pi. I'm gonna go up to 3 pi in x, and I'm gonna go to -4 pi. So this is -pi, -2 pi, -3 pi, and finally here would be -4 pi. So this is the x-axis. The x-axis, there you go. So once I have identified the value of a and the value of d, I can mark these values by using a straight line. You will see later on why this is useful to do. So the value of the amplitude, sorry, I'm going to mark first the value of the axis. The value of d will always represent the axis of my trigonometric function. Because remember, when there is no vertical translation, my axis would always be at 0, right? At the line y = 0. But when I have a vertical shift up or down, my axis moves. So now the axis of my trigonometric function is right here, this green line over here. So let me write this as axis of the function. This is the axis of our function. And then from this axis, I'm going to mark the maximum value and the minimum value. As we said, the maximum value would be at 3, because we're moving from -2, we're moving 5 units up, so we get up to +3. And our minimum value would be from -2, we move 5 units down, and we go to -7. So over here, we would have our minimum values, okay? So this is, let me write, this is maximum value, and this is our minimum value. So that's basically step number 1, okay? Let's read this again. It says, identify the amplitude and vertical translation to determine the axis of the function. We already found the axis. The maximum and minimum values, we already have marked both in our function. So that's it for step number 1. Now, let's move on to step number 2. Let's read what this step is about. It says, identify if the function is sine or cosine, and the horizontal translation to determine the position of the origin point. Okay, so this function is a cosine function, right? So we need to identify if it's sine or cosine, it's cosine, and then the horizontal translation. Remember, the horizontal translation is given by this value over here, right? So let's write that information down. First thing, it's a cosine function. It's a cosine function. Why is this important to identify? Because we would know where this where the parent function starts at, right? So let me write this as like this. The standard cosine function has its maximum when x is equal to 0. When x is equal to 0. That's what we know about a standard cosine function. But now we have a value of c which produces a horizontal translation. The value of c in this case is negative pi. Remember, why negative pi? Because our original formula, let's say, is this one over here. You see that it's always x minus c according to our general formula. So if this is positive pi, it means that the value that it's producing, this positive pi, should be negative pi over here in order to make a negative times negative, and then it becomes positive, right? So pay attention with that. The value of c is actually negative pi. Negative pi. That means that there is a horizontal translation. Horizontal translation. Pi units to the left. Pi units to the left. Okay, so I'm going to use the same graph I already did here to avoid wasting time. I'm going to duplicate this, and we're going to see how this looks like. It should go right here. Okay, so if we know that a standard cosine function begins or has its maximum when x is equal to 0, we wouldn't have to mark this point over here, right? But since there is a horizontal translation, pi units to the left, then I will move pi units to the left, and this is where my original or my starting point would be, okay? That's why this is useful to identify, right? So this is a known point of the graph, which, by the way, is a maximum point. So let me write that down. This is maximum point. So we have identified our first point here, right? By using these two pieces of information, identifying the type of function and if there is any horizontal translation. Okay, so that's it for this step. Let's read the step again, just to clarify. Identify if the function is sine or cosine, and the horizontal translation to determine the position of the origin point. So yes, we have already identified the position of the origin point, which is right there. Okay, so that's it for this step number 2. Now let's move on, I think I'm going to do it here, to step number 3. Step number 3 says the following. Calculate the period to plot the remaining points. So we would have to calculate the period now. And it says midway between two maximum values, there's a minimum value, and midway between a maximum and a minimum value, there's a point on the axis of the function. So that is important information that we should consider. So to identify the period, I would first need to identify the value of b. If we take a look at our function, the value of b is 2/3, okay? So let's write this down. The value of b is equal to 2/3. That means that the period, remember there's a formula for the period. The period is always calculated as 2 pi divided by the absolute value of b. So we know that the period of this function, let me write it, the period is equal to 2 pi over 2/3. Over 2/3. And if we simplify this, the 2 cancels out, for example, this one with this one, and this 3 goes up, right? So the value of the period is equal to 3 pi. Okay, so we already know after how many values this function repeats, right? The period is of 3 pi. I'm going to take this up again. There you go. So once we have identified the value of the period, we can again do our sketch. And now I mark all of the different points using the concept of period, right? What a periodic function is about. Okay, so I'm going to put the graph here. Actually, should be there. Okay, so if our period is 3 pi, that means that after 3 pi, for example, if I look at this point, after 3 pi, I need to have another maximum point, right? So let's see. If I move pi, 2 pi, 3 pi, I'm doing it like this. Pi, 2 pi, 3 pi. So here we would have another maximum point, right? Because we moved 3 pi units, which is our period. Let me erase this. And if I do the same thing to the left, I move pi, 2 pi, 3 pi, then this point over here would be another maximum point of this function. Okay, now I have identified all of the maximum points for this domain defined here. And now let's read again what it says here. It says, midway between two maximum values, there's a minimum value, okay? So this is very important to identify minimum values. If we have this situation over here, midway would be, for example, here. Yes, 1, 2, 3, 1, 2, 3. So midway, we should have a minimum value. So right here, we have a minimum value. And same thing here, right? 1, 2, 3. This is midpoint. So midway, we are having this minimum value right here. Okay, sorry. There you go. Okay. And then it says, for the second part of step number 3, midway between a maximum and a minimum value, there is a point on the axis of the function. So again, if I take a look at the midpoint between these two values, a maximum and a minimum, we're having a point in the axis, right? So midway would be 1, 2, 3. So it's in 1.5 here. So right here, we're having a point in the axis. Okay, and then same thing here, right? Between a maximum and a minimum, we're having this point over here. Between maximum and minimum, 1.5 point over here. And finally, let's see, between 1.5 right here, we're having another point. And I think that's it. That should be fine to make our graph. Okay, so let's identify what we just found here. These are the axis points. These are all minimum points. Okay, and I think that's it, yes. So once we have plotted a series of points, we should be able to do our sketch, right? Step number 4 actually says, connect the points by hand, okay? So with all of these points, we should be able to get a nice cosine function that represents this situation. So using our hands, I'm going to join these points, and we're going to have a nice cosine function, which is the sketch of this graph over here. Okay, so that's how you sketch a function. This seems to be long, but it's actually not. I made all of the different explanations for you to understand this well, but it shouldn't take too much time to sketch this graph. Okay, so this is how you sketch a trigonometric function without using a calculator. So finally, we're going to see this last example in which we're going to do the opposite. We're now given the graph and we want to find the equation of this graph over here. So it says, find the amplitude and period, then write one sine equation and one cosine equation for the function shown in the diagram. Okay, so we want to find a sine function, so we would have to consider the general form, a times sine of b times x minus c plus d, and y equals a times cosine of b times x minus c plus d. These are the two general forms of the trigonometric functions we are studying. So, from the graph, there's a series. Well, we need to find amplitude, we need to find a period, we need to find the value of C and the value of D. So horizontal translation and vertical translation. So from the graph, we can identify all of this information, right? One thing that I noticed, for example, to begin with, we have a maximum value right here. Let me do this with orange. We have a maximum value right here, and then the maximum value again repeats here, right? And what is the distance from this point to this point? This distance actually represents the period, right? The period of the function is the distance from one maximum to another maximum. So this is the period of the function. And if you take a look, the value of the period is 4 pi, right? If we move 1 square to the right, then, and here 1 square to the right, it is easily noticeable that the period is equal to 4 pi. So the period is equal to 4 pi. We already have this important information. Then another thing, the value of D, or actually, yes, the value of the amplitude. To find the value of the amplitude, remember it's the distance from a maximum to the axis, right? We do not know yet what the axis is, right? But we can find that by finding the average between a maximum and a minimum point. You see that the maximum, for example, let me write this information. Maximum occurs at y equals 3, that's our maximum value, and the minimum occurs at y equals -1, right? So with these two pieces of information, we can find the axis of the function by finding the average between these two values. So it's 3 plus -1 divided by 2. This is the average value between both. This is 2 divided by 2, and this is equal to 1. If this is the axis of the function, it means that the value of D of this function should be equal to 1, okay? So here we have one important thing already, the value of D. So now that we know the value of the axis, we can mark this right here using green. Kind of. It doesn't mark well. I'm going to leave it like, I'm going to try to do a straight line here. There. Okay, so this is the axis of the function. And now that we know the axis, we can easily calculate, for example, the amplitude, right? The amplitude is the distance from the axis to either a maximum or a minimum. The value is the same. So let me mark this here. Let me zoom in here. And we would find that the value of A is the distance from the maximum to the axis. Maximum to the axis, so this is value of A, which in this case is equal to 2, right? 2 is the value of A. So we have another important information here, the value of A. The value of D, if you want to remember, it's this distance over here, from the center, from y equals 0 to the value of the vertical shift. D equals 1 in this case. Okay, so we already have, from our graph, we see that, let me write all of this information down. Let's start first with the cosine function. The cosine function. For the cosine function, which is this one over here, you can find the amplitude by performing the following. It's instead of 3 plus -1 divided by 2, now we're going to find 3 minus -1 divided by 2. It's the maximum minus the minimum divided by 2. So this is 3 minus -1 divided by 2. So this is 4 divided by 2, which is equal to 2. So the value of A is equal to 2. You can find it this way, or you can find it graphically as we did before. Okay, then we already know that the period of this function is 4 pi. If the period is 4 pi, remember the formula for the period. Period is always equal to 2 pi over b, right? So if the period is 4 pi, then we can solve the value of b. We can find the value of b, and we would see that this is, let's see if I have space here, this is b is equal to 2 pi divided by 4 pi. So the pi's simplify, and 2 divided by 4 is 1/2. So the value of b is equal to 1/2. So there we have the value of a, we have the value of b, and we also already have the value of d. So the only letter we're missing is the value of c. And you will see that in this exercise we want to find one sine equation and one cosine equation. And the only value that will change from one graph to another is the value of c. That's why we're leaving the value of c for the end, okay? So, how do we find the value of c? The value of c represents a horizontal translation of the function, right? If we zoom in into this equation, and remember we're working now with a cosine function. If we zoom in here, and you should remember that a cosine function, the standard cosine function, always begins at its maximum point. So when x is equal to 0, the function it's at its maximum, right? But we see that the maximum is actually at this point over here, which is 1 squared to the left of this graph. So if we calculate what 1 square represents, then we would have the value of c. It would be that number of steps to the left, right? You see that here we have 1, 2, 3, 4 squares. 1, 2, 3, 4. That means that each square represents pi over 4, right? That means that the function is displaced pi over 4 units to the left. Okay, so that's how we obtain the value of c for a cosine function. So let me write this information down. We're going to say that the standard cosine function starts at its maximum. So c represents the horizontal translation, right? Translation. From the graph, we have observed that the value of c is actually negative pi over 4. That means it's displaced pi over 4 units to the left. So the function is translated pi over 4 units to the left. Okay, so here we have the value of c. So now we can build our complete cosine function, which would be, let me write it here, final equation, or final function actually, not equation. Final function is 2 cos, our value of a is 2, our value of b is 1/2, our value of c is negative pi over 4, and our value of d is 1. So the final equation would be 2 cosine of b, which is 1/2, times x plus pi over 4, we're moving to the left, and then plus the value of d, which is 1, plus 1. So this would be the complete cosine equation for this graph over here. Okay, for this graph. We're gonna later graph this in order to see if we're doing this correctly. Okay, so let me make the clarification here that this distance over here, from here to here, represents value of c for cosine function. Okay, so finally, this video got a little bit long, but I need to finish this. So finally, we need to find now the sine function. So for the sine function, we're gonna do exactly the same thing, and actually you should see that all of the letters except C are the same. Okay, so for the sine function, the value of A is still equal to 2. The value of D is still equal to 1, right? The axis is still this one over here, the green one there. And the value of B is still 1/2, right? Because the period of the function is not changing. The period of the function is not changing. So the only thing that's changing is the value of C. To make the analysis, we're going to do the same thing. We're going to zoom in here. And if you remember from a standard sine function, the standard sine function begins at the point 0, 0, right? Which would be this one if we consider the vertical translation. But it starts at 0, 0, right here. And you should know that the sine function always goes up at first and then it goes down, okay? So the horizontal shift would be this distance over here. This function is beginning right here for sine. So that distance would be the value of C for the sine function, okay? It is a mistake to consider this point over here. Why? Because if you consider this point over here, the function is going down after it begins, and the original sine function goes up after it begins. So it would be a mistake to consider that point over there. So we should look at this point right here in order to find the value of C for the sine function. Okay, so let me mark this here. This distance from here to here, this distance would be the, right here, it's the value of C for sine function. So once we have this plotted, we can calculate how much is this. It's negative pi minus pi over 4. That would be the value of C. So let's go down. We're going to write this down. The value of C would be let me write the explanation first. It says the standard sine function starts at the origin, right? Which is 0.00. So C is equal to negative pi minus pi over 4. If we look at the graph, you would see y. So the value of C is equal to negative 5 pi over 4. This is the value of C for the sine function. So once we have all of the letters, we can write the final function. The final function, which is y equals 2 times sine of B, which is 1/2, times x plus 5 pi over 4. And this is all plus D, which is 1, plus 1. Okay, so this is a complete sine function that represents this graph over here, this one over here. So you see that for any type of trigonometric function, you can find either the sine or the cosine function. It just, the values are the same. The only thing that varies is actually the value of C. Okay, so sorry for the long video, juniors. I hope this was clear. If not, please let me know. We're going to clear doubts in future live sessions. Thank you for your attention and see you.